Rodolphe Thiebaud, professeur à l'ISPED, et j'ai l'honneur de diriger donc cette session avec deux parties. Une première avec une présentation de Jonathan Sterne, présentée tout de suite, et suivie d'une table ronde qu'on espère très interactive. Alors bien sûr, vous pouvez utiliser le logiciel et attentif aux questions que vous posez, mais vous pouvez aussi les poser en direct, sachant que dans le cadre d'une table ronde, c'est pas mal aussi quand c'est assez interactif. J'aurai l'occasion donc d'avoir 5 intervenants avec moi pour cette table ronde. Donc on va commencer par une présentation sur l'inférence causale, ce qui n'est pas aisé, et c'est une session sur l'enseignement. Et justement, à ce titre-là, nous avons demandé à Jonathan Sterne de venir nous faire une présentation sur ce sujet. Pourquoi? D'abord parce que ce professeur de l'université de Bristol est très connu dans ce domaine. Il est connu dans d'autres domaines, y compris méta-analyse, bref, dans plusieurs aspects de la méthodologie en épidémiologie et en statistique. Et surtout il présente avec une clarté qui est absolument incroyable, que ce soit dans le cadre de topos de recherche ou d'enseignement. Et donc on le remercie vivement d'avoir accepté de venir faire cette présentation. Mais je dois dire qu'on le considère quasiment comme un ispédien. Et je pense que la directrice de l'ISPED ne contredira pas. Jonathan a la particularité de comprendre très bien le français et de pouvoir bien sûr s'exprimer en français, mais il aime bien aussi parler en anglais. Donc il va sans doute nous faire ce topo en anglais. Vous pourrez poser vos questions en français et en anglais et on gérera la traduction comme tout à l'heure. So thank you very much, Jonathan. And so now we are going to hear you. With a great pleasure.
Merci, Rodolphe. I will try to achieve clarity, but probably not at the level that you just said. So this is my title. And this is all I was told. This is your title. So I had to decide what I was going to talk about. So I thought that, and I was really pleased to receive this invitation for two reasons. Firstly, because I love coming to Bordeaux and to see the various colleagues who I've worked with over the years. So that's one very good reason. And the second reason is that my colleagues have been thinking a lot recently. We're launching master's programs at the University of Bristol in public health and epidemiology. And I've been thinking a lot about this topic. How should we change? Given the methodological developments that there have been in the last maybe 25 years, how should we change the way we teach our students? And here's the problem. You all know, I know, you know, everybody knows, the whole population knows that association is not causation. All your students, before they ever get here, they know association is not causation. But the problem is, we want to talk about causation. Why are we doing public health? We're doing public health because we want to change things to improve health. We want to know about cause and effect in order to do the right things to improve health. That's the problem. So how do we do causal inference? Well, I'm a British academic, and so I make my causal inferences by reading the Guardian newspaper. Here's an example from the Guardian newspaper. It's a very useful causal inference for public health practitioners. As it happens, do you eat Brussels sprouts in France? Yeah? I'm in a minority of the population because I really like Brussels sprouts and broccoli. And so this is good news for me. Eat your Brussels. Scientists say these vegetables, in fact, cruciferous vegetables, provide heart benefits to older women. Fantastic. Here's what the article, we adjusted for blah, 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 lifestyle cardiovascular disease. There was a protective association. What's this word protective association? Protect, that's causation, right? Association is not causation. What else did they say? This was only an observational study. A causal relationship cannot be established. But dietary guidelines should highlight the importance of increasing consumption. That's a causal statement, right? If you increase your consumption of cruciferous vegetables, you will reduce your cardiovascular disease. Okay, but this is just the newspapers. It's the British newspapers. Everybody knows how terrible the British newspapers are. French newspapers are not like this. Surely this isn't true. Unfortunately, this is true in scientific journals as well. So I hope there's no author from this study in the room, but here's a study, association between active commuting and incident cardiovascular disease, cancer and mortality, prospective cohort study. This is the UK Biobank, 500,000 people, really narrow confidence intervals. What did they say? I can't read it. They aimed to study association. Okay, they aim to investigate the association between active commuting and incident cardiovascular disease and cancer and all-cause mortality. Okay, that's fine. What do they find? Active commuting was associated with a lower risk of these outcomes. Okay, they found an association. Okay, but then they say initiatives to encourage and support active commuting could reduce the risk of death. This might be causal. Maybe we should do something in the world. Okay, so that's the paper. We all know that we have to be cautious in the paper. Then the BMJ, they publish a news article. Cycling to work has substantial health benefits. Fantastic. Cycling to work is linked to a substantial decrease in the risk of developing and dying from cancer or heart disease. What do the authors say? These findings, if they are causal, suggest that population health could be improved. They want to make a causal inference. The authors are talking about causal inferences, although in the abstract they mention mainly causation. And then you get your editorial. Active commuting is beneficial to health. The findings from this study are a clear call for political action on active commuting, which has the potential to improve public health, blah, 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 blah. Yeah? So this is how we do science at the moment. We talk about causations and then, well, we end up with a BMJ. Active commuting is good for health. That is public health now. This is indefensible. This is not scientific. We study associations and then we make claims about causation. Now, it's not a coincidence that we're in this mess. Thinking about teaching again, what are the tasks of medical statistics and epidemiology? First, description. Really important. In the last talk, we saw some descriptions of patterns of migration and requirement for health professionals. In the UK at the moment, we're seeing the first decreases in life expectancy that have been seen in many decades. The start point is always description, and we need to be good at that. And then there's prediction, and I'll come back to that at the end. Prediction is the study of associations. If I see these sorts of characteristics in a person, what is likely to happen in the future? And then there's causal inferences. And the problem is that traditional statistics, my discipline, does not formally distinguish between prediction and causation. If I fit a logistic regression model over any other model, I'm doing prediction, but I don't know when I can use the results of that model to make a causal inference. The language just isn't there. So it's the fault of my discipline and our disciplines that everybody gets so confused. The problem is that seeing, for example, an association between active commuting and improved health is not doing. I increase my active commuting in order to improve my health. So our traditional disciplines do not distinguish between association and causation formally. They do not distinguish between seeing and doing, which is why we get so confused. So we know that association is not cause. We want to talk about causes, but we can now define what we mean by a causal effect, relate association to causation, and in doing so, in understanding the relationship between association and causation, we can understand the biases that may undermine causal inferences, both from randomized trials and observational studies. So what do I mean by causation? Well, when I talk about causation, I really am thinking at an individual level about what will happen to a person if they do one thing, or I treat them with one thing, compared with what would happen to the same person if I did the other thing. What would be their outcome if treated? What would be their outcome if untreated? What would be their outcome if they increase their active commuting? What would be their outcome if their active commuting stays the same as now? Causal inference is about comparing one thing in a person with another thing in the same person. But that's a problem, because I don't get to see both things. I either treat them and see what happens if they're treated, or I don't treat them, or I give them a comparator interventions and I see what happens. So at least one of these outcomes is potential, or counter to fact, or counterfactual. I don't see both outcomes. That's why causal inference is a big problem. Or at a population level, I can do the same thing. What would happen on average in the whole population if I treated all of them? What would happen on average in the whole population if I didn't treat them? If I can make that comparison, I can talk about the population effect of a treatment. But the problem is that for an individual, I only get to see one of those two outcomes. So that I think is a really quite intuitive way of understanding or explaining to our students what we mean by a causal inference and why it's difficult to make causal inferences. So that definition is one of the first thing that I think we need to explain to our students. And the second thing is that through directed acyclic graphs, or DAGs, and the associated theory, because they're underpinned by mathematical theory, I can now understand the biases that may undermine causal inferences. So DAGs, because they're directed, they've got arrows that are in the direction of causality. They're acyclic because if I follow causality, I can't get back to where I started. Causation happens forwards in time. Okay? If I usually have something to drop at this, here we are. If I hold this and I open my hands, the memory stick drops to the floor and the cost of the meeting is now increased. Okay? So causation happens forwards in time. If A causes B, then B must happen after A. Maybe 1 microsecond, maybe 100 years, but it happens later. And because of that, if A causes B and B causes C, I can't go back and have C causing A. Acyclic graphs. And the point about these graphs is that they're not a solution to everything, but they do allow us to explain concepts in causal inferences in a way that I find really helpful. And they're underpinned by a mathematical theory. So I can make statements about these graphs knowing that the maths behind it justifies the statements I want to make. Now, what are they for? They're not a magic solution, okay? I think there's an idea that if I just draw a graph, then magically I can make a causal inference. Causal inferences from observational studies, I'll come to the distinction between randomized trials and observational studies in a moment. Causal inferences from observational studies require that I make assumptions that I cannot test. I have to make an assumption. My graph is used to document the assumptions that I want to make and deduce the analysis that I should do. So the purpose of these graphs in the first instance is to say, here's what I believe about the causal relationships between the variables in my data set and maybe the variables that I didn't measure. So I document my assumptions in a graph. Now, the rules of the graphs allow me to identify whether there is confounding, identify the variables that need to be controlled if I'm going to deal with the confounding, and identify variables that I should not control for because controlling for them will cause bias. So I could be simple or I could be complicated. Here's a particular example to do with healthcare utilization. In traditional epidemiology, as I learned it, I couldn't answer this question. What variables do I need to estimate need to control for to estimate the causal effect of health service utilization on child mortality? I don't know. If I can't measure financial resources, can I still control the confounding? There used to be no answer to these questions, but these questions can all now be answered through the rules of directed acyclic graphs. I still need to measure the variables. I can't prove that my assumptions are correct, but I can document my assumptions and deduce what I should now do, and deduce whether I can control the confounding. So, causal graphs allow us to say something about causation. We see associations. Let's assume now that we're studying a big population. So let's forget about the role of chance. Of course, an association can always arise by chance. But if I study UK Biobank and 500,000 people, then I see associations. I can be confident that it wasn't just chance. So association is not causation. That's not a helpful statement. But I can now understand why I see associations in the data. And the first reason that I see an association between two variables, perhaps E for exposure and D for outcome, is that they are cause and effect. Causal effects lead to associations. You all know that, right? This is a randomized trial because there's no common cause of exposure and outcome. Let's do a randomized trial on 50,000 people. Maybe I randomize them to 25,000 people get antihypertensive medication and 25,000 people get placebo, okay? What will I see if I follow them all up for 20 years and look at the incidence of a heart disease? I will see an association between antihypertensive medication and heart disease. Causal effects lead to associations. Antihypertensive medications have a causal effect on heart disease because they reduce blood pressure. Okay? Blood pressure is on the causal pathway from antihypertensive medication. Actually, it says lung cancer because I changed the example. Should say heart disease. Unless maybe you want to go and publish this and maybe you'll get a prize, but okay, should say heart disease. Okay? If antihypertensive medication is on the causal pathway, what will I see? I'll see an association between medication and blood pressure and between blood pressure and heart disease. Why did those associations arise? Because of causal effects. The first reason for association in my data is cause and effect. What's the second reason? You all know this. The second reason is that the two variables share a common cause. That's confounding. Okay? If a variable C affects exposure and also affects the outcome, it will cause an association between exposure and outcome. So, I've now got two reasons that I might see association in the data. And now I can start to talk about the fundamental role of randomized trials in making causal inferences. I can only avoid confounding if I randomize. Because by randomizing, I break the link between prognostic factors that affect the disease outcome, and exposure or non-exposed, or treatment or comparator treatment. Okay? By randomizing, I ensure that there is no association of treatment with measured or unmeasured prognostic factors, other than by chance. In a randomized study, the individuals who are allocated to the intervention group can be considered to be exchangeable with the individuals who were randomized to the control or comparison group. There are no systematic differences between the two groups. So in a randomized study, I'm prepared to use the outcomes in the comparator group as surrogates for the outcomes I didn't see. I wanted to see what would have happened in the treatment group had I not treated, but I can take the outcomes in the comparator group and say, okay, those will be the same as the outcomes I would have seen in the intervention group. This is how I can link the idea of counterfactual outcomes with things that I can observe in the real world. So, we can estimate causal effects. We can identify causal effects using data I can see, either when there are no common causes, which is when I did a randomized trial, and I didn't screw it up any other way, or I'm in an observational world, there are common causes, but I measured enough data to control the confounding. In the terminology of directed acyclic graphs, I say there's enough data to block the backdoor paths. In a more traditional terminology, I say there is no unmeasured confounding. If, based on my assumptions, there is no unmeasured confounding, I can make a causal inference. And if I'm going to try to make causal inferences, I should be clear about my assumptions and whether I believe I can control the confounding. Now then we have statistical methods, and they're just ways to control confounding. I still think that the most intuitive way to explain confounding to our students is explain it through stratification. Explain that if I stratify on the confounder, then within a stratum in which the confounder does not vary, there can be no confounding. But I don't care. Stratification, standardization, regression models, propensity scores, inverse probability weighting, they're just there to control confounding. So I should explain the methods in terms of what they can do, and I don't want to start pretending they're a magical solution. Propensity scores aren't a magical solution to control confounding. They're just a method of controlling the confounding that has some advantages. Now, there's a third reason that I may see an association between an exposure and an outcome. And this is less well understood. The third reason is that the variables E and D share a common effect, and we condition on it. And this is the problem that is now called selection bias. Here's a real example from a study I was involved with. This was not a causal inference study, this was a prediction study. So it was a study of urinary tract infection in children aged less than 5 years attending primary care. So we took the children who were eligible for the study were acutely ill individuals who were attending their family doctor, and we recorded symptoms or signs, and then they gave urine samples, and then the urine was cultured, and we identified bacteria the causal for a urinary tract infection, and we looked at prediction. And we developed a prediction rule, and we found that pain or crying passing urine was associated with a UTI, smelly urine was associated with a UTI, history was associated with a UTI. And then we found a strong negative association between severe cough and UTI. And my colleagues started saying, well, this is really interesting. Maybe biologically, if a child has a severe cough, then there are immunological processes that protect against the UTI, and they started talking to me about cytokines and thinking about the discussion, and I went, no, this is selection bias. And they had no idea what I was talking about. And I had to explain to them that if our study was done in children who attended primary care, severe cough causes you to attend primary care, UTI symptoms cause you to attend primary care. And if now I condition by only looking at the children who attended primary care, then if these things are independent in the population, they will be negatively associated in the children who attend primary care. Now that's useful information for a doctor, because if a doctor sees a child with a severe cough, they really are less likely to have a urinary tract infection. It's useful information for prediction, but it's nothing to do with causation. And that is the phenomenon called selection bias, which is defined as the bias that arises when the parameter of interest in a population differs from the parameter in the subset of individuals who are available for analysis. It arises when we condition on common effects in design or analysis. And you may these days, because common effects in directed acyclic graph terminology are known as colliders, this is also called collider bias. Because of this phenomenon, because of the language of causal graphs, I can now have a conversation about when does missing data in a randomized trial lead to bias? I didn't used to be able to quite explain that. I know that often in a randomized trial I can't follow up all the individuals. But I can now talk about when the subset of individuals in whom I measured the outcome will give me a biased estimate of the causal effect of intervention on outcome. So this includes all this list of different biases: loss to follow-up bias, non-response, missing data, volunteer bias, self-selection, healthy worker effect, so on and so on. They're all examples of this single phenomenon of conditioning on a common effect. And very importantly, this is completely separate from confounding. Confounding involves biases that are inherent to the source population. I could study everybody, but there's a common cause of exposure and outcome. Whereas selection bias is about a difference between the the data available for analysis and the target population. And one of our jobs as teachers is to explain to our students the sad truth that this is completely confused in the scientific literature, that people talk about selection bias, but they mean confounding. And here's another example. There are plenty of examples, but a nice paper in JAMA a couple of years ago, same phenomenon, that risk factors for a condition tend to be inversely related to its recurrence. So smokers have better prognosis than non-smokers after a heart attack. That's crazy, but people start to say, oh, maybe there is some protective thing that's going on. Among patients with heart failure, better survival has been associated with obesity, higher blood pressure, higher levels of cholesterol. Might this be a biological phenomenon leading us to new causal, new interventions? No. This is because when we look at people with established disease, we distort the relationships between the predictors of the disease in the first place. So smoking causes heart attack, older age causes heart attack. In people who have heart attacks, smokers are younger than non-smokers. Sorry, yeah, the smokers are younger than the non-smokers. So these causal graphs allow me to talk specifically about the biases that can affect our research. These are the things I need to teach the students. They could be reverse causation, confounding, which is the presence of common causes, and conditioning on common effects in design or analysis, selection biases. And I can now explain that there are these three sources of association. In the presence of common causes, I should condition on those to make my causal inferences, but I should avoid conditioning on common effects in either design or analysis. And in some circumstances, there's nothing I can do. I can't correct for the selection bias, or I can't control the confounding, so I can't make a causal inference from my observational data. So we tend to teach our biases by sort of this horrible long list of different things. We can now not burden our students with these long lists. Let's get rid of all those. And instead, we can talk about three types of bias: confounding bias arising from common causes of exposure and outcome, selection biases arising from conditioning on a common effect, and information biases, which I haven't talked about, arising from measurement error. And I can now explain all those different words and phrases and descriptions in terms of these three biases. It's simpler, it's easier, and it's much clearer when we think in these ways. And then you'll all have taught the traditional hierarchy of evidence. We need to get rid of this, because it's not about the hierarchy of evidence, it's about the biases that can affect our particular study. So, of course, randomized trials have got one characteristic that distinguishes them from observational studies. If the randomization was done well, then we have no confounding. That's incredibly important, but we can still have biases in our randomized trials, and we need to explain those, and indeed we can have conversations about the biases in our randomized trials based on causal graphs. We can explain what we mean by those biases and how they can be avoided and why they might occur. And similarly, for non-randomized studies, we can think about the biases that can occur when we try to make causal inferences from our observational studies and start to assess our observational studies for the presence of these biases. So in terms of the journey for students, my start point is to ask, why are you doing this study? Is it for prediction, or is it about causation? These are two completely separate problems, and everything will be easier if our students understand that these are separate problems. So for prediction, which of course includes prognosis and diagnosis, the students need to know how they can design a prediction study. How do I develop a prognostic model with all the choices of non-linear effects and variable selection that are involved. How do I measure the predictive ability of a prognostic model? They need to know about the importance of external validation and transportability and calibration. And then there's tremendous excitement about big data now, digital health. All governments, policymaker, everybody seems to believe that we just have to have access to healthcare data and everything will be fine. So our students need to understand the potential of big data, but they also need to understand that machine learning and artificial intelligence are about prediction. They're not about causation. I can go away and get data on 10 million people, but if I didn't measure the most important prognostic confounding factor, I can't make a causal inference. I may be great at prediction, but prediction is not causation. Causal inference. These messages should start, in my opinion, in lecture 1 of any course on public health or epidemiology or medical statistics. Go beyond association is not causation to explain associations arise because of cause or effect or bias. As I hope I've convinced you, randomized trials are the start point for causal inference. And really, by comparing what we have to the randomized trial that we would like, that should be our start point for understanding whether we can say anything about cause and effect in our observational data. I hope I've convinced you that causal graphs help us to explain these concepts. Lots of real examples help to explain, particularly when the speaker doesn't confuse lung cancer and heart disease. And finally, the methods should be taught, should be motivated by their ability to deal with specific types of bias, not as just something clever that we might be able to do. Thank you.